Okay, hello everyone. I'm just going to make another recording showing you how to run multiple regression analysis using SPSS. So in this video, I'm going to focus on running a standard multiple regression analysis. So this is where we put all our independent variables in to the model at once. And the data set that I'm using is a data set that's featured in the Andy Field textbook. It's called albumsales.sav, and it's basically a load of data. I don't know if it's made up, but it's around looking at which variables, which factors might predict the sales of a music album. So the dependent variable, the output variable is how many thousands of units a particular album has sold, and the predictors, the independent variables that we're looking to see if they can predict these sales, in this case are advertising budget. It's called adverts in this particular column on the data file. Airplay, which is the number of times the song or songs have been played on the radio, and image, which relates to the band's image. So advertising budget is in thousands of pounds, measured in thousands of pounds. Airplay is kind of number of times the song's being played, and band image is rated on like a Likert scale from 0 to 10, with 10 being better than 0, like higher scores being better. Okay, so what we'll do is run a standard standard multiple regression on this data, see if these three things can predict album sales. So to do that, it's similar to linear regression, simple linear regression, and we click on Analyze, we go to Regression, and we again select Linear, and it gives us this pop-up box that we've seen before, and our dependent variable in this case is album sales, so we're going to move that across to the dependent box. And previously, when we just did a linear regression with one IV and one DV, we moved our independent variable over into this box. But you can see in brackets, in parentheses, it's got an S after independent. So we can basically put more than one independent variable in there. So I'm just going to move all three of those variables across into that box. Okay, and then the next thing I'm going to do is click on the statistics button, and brings up a new pop-up box, and a couple of things by default are already selected. That's estimates and model fit. We'll leave those selected, but I'll also ask for descriptive statistics in this case, and click continue. And one other thing we'll do whilst we're on this particular box is click on plots, and we'll ask for a plot of the residuals, standardized residuals. So if you highlight Z residual, put that in this Y box here, and then Z predicted, so the Z transform predicted scores, put that in the X box and click continue. What that will do is give us a scatter plot of the residuals, so we can look to see if we've got if our data's we've got a fairly even pattern in our data. Okay, so all we need to do now is click OK, and that will run this analysis for us. And as usual, let me make this window bigger. You get the output pop-up window from SPSS. The first table it's given us is some descriptive statistics. There are two things we'll do, and then we'll look at the actual results of the model. So there are a number of assumptions you have to check when you're running a multiple regression analysis. There are a number of assumptions you have to meet, and there are 6 altogether, and it can take quite a while to set it up to check all those assumptions. So we're going to assume that mostly for this data set the assumptions have been met, but what we will do is we'll do a quick check on a couple of things just to make sure we're kind of on the right lines and we don't have any major issues. So the first one that we'll do is look at this. It's giving us a table of correlations between all the variables, And a couple of things we can look at here is see whether the DV album sales is strongly correlated with any of the independent variables. And if you look at them, there's two of them are quite strong. One of them's kind of a medium correlation. So that's quite a good thing. Just looking at that gives us some indication that there is going to be some sort of relationship between our DV and the IVs. So we might find we've got a significant model, and we can use those independent variables to predict the dependent variable. But we will have to look at our results to confirm whether that is the case. The other thing that is worth looking at on this correlation table is the correlations between each of the independent variables. So the correlation between advertising budget and radio plays, and the correlation between advertising budget and band image, and the correlation between radio plays and band image. Okay, so there are three variables, there are three sort of correlations to consider, and with the independent variables in this model, we don't want them to be too highly correlated with each other. If they are, we potentially have a problem known as multi-collinearity, where we've got kind of two variables that are really capturing the same amount of variability. They're sort of measuring the same thing, so to speak. Okay, and in this case, if we look at advertising budget and the number of radio plays, it's got a correlation of 0.1, and it isn't significant. Advertising budget and band image got a correlation of 0.08. Radio plays and band image has a correlation of 0.18. So all of them are fairly small correlations. That's a good thing. We should feel quite confident based on that we don't have an issue with multicollinearity in the data. Okay, so the next thing we should do before we look at the actual output is look at that residual plot that we asked for. And if you remember, we kind of talked about this with linear regression. It's useful to get these standardized residual plots of standardized residuals against standardized predicted values, and it'll give you an idea if you have issues around homoscedasticity or constant variance. And what you're looking for is a fairly even spread of data points around this horizontal zero line here. So if the data points, the residuals, are fairly evenly spread up above and below the line, such that you could almost draw a rectangle around them, then that's a good thing. And in this case, it looks like they are fairly evenly spread above and below the line. They're not all clustered at the bottom below the line, or all at the top above the line, or anything like that. There's no funnel shape to them, so you've got more variability on some end of the scale compared to the other. So that's a good thing. In this case, we can see we've got a fairly even pattern both above this horizontal zero line here and below it. And the other thing to look at is to see if we've got any outliers, any extreme scores, any extreme values, because we know that they can influence the position of the regression line or the slopes of the different variables in relation to the DV. So an outlier, we would be talking about anything that's greater than 3 standard deviations above or below the mean, and there are very few in this case. There's maybe one at the top here that's above. There's certainly none that seem to be anything towards -3 standard deviations. But that one data point is not going to cause us too much trouble, so we're pretty confident we've got a fairly even spread of data, and our data points are not too highly correlated. Okay, so let's look at the output then for this multiple regression model. So the first thing we could do really, I guess, is look at the ANOVA table to see how well the model fits the data. So we fitted this model, and the ANOVA test is checking to see whether the slope of the regression line is significantly different to 0. So does fitting this particular model that we fitted using the slopes, the coefficients that we've got, is it better? Is it a better model for the pattern we see in the data than just using the mean value of the dependent variable, the output variable, the outcome variable? So the mean value of the variable on the y-axis. And as you can see here from this table, we've got an F value of 129.498. So 129.50 if we round that to 2 decimal places. And the significance is P is less than 0.001. So we've got a highly significant result there and a very large F ratio. So what that's telling us is that fitting this model to the data is better than just using the mean value of album sales when you're trying to predict album sales in some way. So better than using just a flat line based on the mean. So using the mean as a model, this regression model is much better. It's a much better way for us to predict scores. Okay, so with that done, another thing we can look at is we know we've got a significant model, so we could then look at this model summary table, which is just above it. And if you remember, this is our model. This is also gives us a good idea of how well our model fits the data. What we're interested in is the R squared value, and as you can see, it's 0.665. So what that's telling us is the amount of variability in the dependent variable that's explained by fitting this model with these 3 independent variables is about 66% of the variability in scores. Okay, so that's extremely high. That would be a very good model if you found a result like that. It's telling us that we can explain a lot of the difference in album sales using these 3 predictors: band image advertising, a number of radio plays. Okay, so that's all pretty good. Well, it's looking like we've got a really good model. So the last thing we want to look at is the coefficients table. Just down here, and if you remember, this gives us unstandardized coefficients, which are the intercept and the slopes for each of the independent variables, sort of line slopes essentially, in this unstandardized B beta column here. And those are quite useful. Those are the things that we would put into our regression equation of the form y equals a plus b times x plus b times x2, etc. And if you remember, when we did linear regression, you've got these 2 columns at the end, this t-test, and what that's testing is it's looking to see whether each of the independent variables is contributing to the model in a significant way. So is it a significant predictor of the dependent variable? And if you remember, when we did linear regression with only 1 independent variable, if you get a significant ANOVA result, you've got a significant F value, it tells you you're going to have a significant T value as well, because there's only 1 predictor in the model. The model's significant, so the predictor has to be significant. With multiple regression, this T statistic is much more useful because it tells us the contribution of each individual predictor. So in this case, we can say that advertising budget in thousands has a T value of 12.261 and a probability of P is less than 0.001. So that's a statistically significant predictor to the model. Number of plays on the radio has a T value of 12.123 and a P value of P is less than 0.001. So again, that's another statistically significant contributor to the model. So radio plays and advertising budget are both significant contributors. And then band image, if we look at the T statistic for it, is 4.548 and P is less than 0.001. So that is also a significant predictor in this model. So all 3 of them are significant. It's not always the case that they are. Just one of those might have been, just 2 of them, 2 of the 3. and sometimes all of them. In this case, all three of them are. So that's kind of useful. It's interesting to know, and we know all three are significant predictors to the model. And if you remember, when we look at our unstandardized betas, it gives us in the row labeled constant, it gives us the value of the intercept. So that's the value of the dependent variable when you input 0 for all your independent variables. So in this case, it's negative 26.61. The slope, the other unstandardized coefficients are the slopes of the line that relate to each of the individual predictors or independent variables. So you can see that advertising budget has a slope of 0.085. Number of plays on the radio has a slope of 3.367, and band image has a slope of 11.086. Okay, so it's kind of good to know that, and we know they're all significant predictors. But if you remember, with the unstandardized coefficients, where they are all measured on different scales, it becomes difficult to compare them. So yeah, if you just eyeball these, it's hard to say, is 11.086 a more significant contributor than 0.085? We don't know, because they're measured on vastly different scales. So the thing to look at to tell us the extent to which a independent variable is contributing to the model is the standardized coefficients, this beta column here, the third one along. And if we look at those, what that's done is it's converted them all onto a standard score, so we can then compare them and their influence. So what you can see here is for advertising budget under the standardized coefficients, we've got a coefficient of 0.511. For number of plays on the radios, we've got a coefficient of 0.512. For band image, we've got a coefficient of 0.192. What that tells us is that for each one unit increase, so one standard deviation increase in advertising, then album sales increase by 0.511 standard deviations. So each one standard deviation increase in advertising budget results in a half a standard deviation increase in album sales. For plays on the radio, a one standard deviation increase in number of plays on the radio results in a increase in album sales of 0.512, or very similar, just over half a standard deviation in terms of number of album sales. For band image, a one standard deviation increase in band image results in an increase in album sales of 0.192, so just about a fifth of a standard deviation. Okay, so what you can see from looking at these three is that advertising budget and radio plays, they are influencing, they're contributing to the model more than band image. Band image is less important, but you wouldn't have known this if you'd have just looked at the unstandardized coefficients. If you look at those, it looks like band image is actually it has a much larger value than radio play and advertising budget, but the important things to remember is they're measured on quite different scales. Okay, so those are the important things to think about, to take away from this, that once we've run our analysis, we can check the correlations. We don't want our IVs to be too highly correlated. We can look at the residual plot. We want them to be fairly evenly spread, a nice even pattern above and below the 0 line for the standardized residuals. We can then look at our ANOVA table to see if we've got a significant model, if it's better than just using the mean value of the dependent variable to describe the pattern of the data. We can look at how much variability the model explains by looking at the model summary table at the R squared value. and then we can look at the contributions of each individual predictor by looking in the coefficients table. Okay, I'll stop now because that was a longer video than I expected it to be. Okay.